Hi everyone, welcome back to this channel. Today we are going to talk about a very interesting and very popular problem in a tree, which is maximum depth of a binary tree. Now, before moving to the problem statement, I will explain as simple as possible. Even if you don't have knowledge about tree, don't worry, I will explain it very simple way. Now, let's understand the basics. So what does mean by binary tree? Let's see it quickly first and then we'll go to the problem statement. So what is basically a binary tree? Binary tree is nothing but assume it as a family tree. So a node, this is called as a node. A node, at most, it can have two nodes. At most, remember this word carefully, at most two, which indicate that it can have zero node, it can have one node, it can two node. At most two. So which means that every branch, every node can have either a left or a right. That's it. It cannot have more than two children. That's the concept of binary. You can get from the name what is mean by binary. So binary always indicates 0 and 1, which is 2, right? That's why you can simply keep in mind that binary tree is nothing but at max you can have two children. So you can see this grandpa has two child and this first child has two children for him. At max everybody has two. So he can have one children and he can also have two children. But at max he can have two or 0 or 1. These are the possible node you can have. And I hope you understand what is meant by binary tree. And we'll talk about the what is mean by depth of a tree. This is the important thing for this particular problem. So just imagine like you are walking onto the tree. Walking onto the tree and you need to find the maximum step to reach the longest path. That's the task. Remember the word maximum path. You need to find the maximum number of steps to get from this particular place to the down. That's it. This is the basic question. And now let's see how to solve this particular problem. And I will answer to the answer to this particular problem in my explanation. Now just imagine like this. You just standing here and you need to find the longest path. Like how much steps it will take to down. And you can call this problem as what is the height of a tree, and what it could be asked like what is the deepest point in a tree. For all this particular word, the solution is going to be similar. Now let's see how to solve this particular problem. Now first we are going to talk about the DFS solution, which is common in all trees problem, and then we'll talk about how to solve this problem using BFS method, a level wise order, and then we also try to see how to solve this using iterative DFS. Okay. Now, basically, if you take a DFS solution, it comes with recursion, right? So whenever you use recursion, you need to care about two things. One is going to be actually three things, but for this kind of problem, you can have two things. So which is the first one is going to be the base case, and next you need to care about what is the recurrence relation. These are the two things you need to keep in mind. And if you solve problems in backtracking, you also need to care about the goal. But right now we don't need to care about those things. Let's think about only two things. One is base case, one is recurrence relation. That's it. So let me take this tree for you guys to explain it. I'm going to copy this tree. I'm going to paste it over here. Now let's think about base case, guys. So when do you conclude the tree reaches at the end point? When do you conclude it? So when you conclude is when you reach the leaf node. If you go to the leaf node, there is no other way to go, right? There are no other way to go. If you go to all the leaf node, there are no other way to go. So what could be the base case is if the node is none, you can simply return a 0. So this is going to be the base case. If node is none or null, so let's keep null, then you can simply return 0. This is the base case. Now if you talk about the recurrence relation, it's very simple. Just think logically. You are standing over here and you are just taking this particular path. Okay, you're taking this particular path and you cannot conclude that this is the longest path until you reach every other path, right? So you need to visit every other path, which means you need to go on the left side as well as the right side. Then only we can conclude which is the longest path. So just think this logic in a mind. The recurrence relation is very simple. 1 plus maximum of t of left. Let's assume t is a function, and t of left plus t of right. This is going to be the recurrence relation, very important one. This particular line you can write the answer, very simple. Now let's understand deeply about this particular recurrence relation, guys. So what I mentioned is we need to visit two different paths, right? One is left, one is right. Then we need to conclude which is the maximum path, and this one. So what do I mean by this one is, let's say you're standing at this particular level and this particular node is also valid. I need to conclude in this answer. So every node is valid, so every node has value 1. Okay, now if I calculate the longest path, which is going to be the longest path in this particular answer, is 1. So this is going to be the longest path. If you count how much node here, 1 2 3 4, the answer is going to be 4. This is the maximum path you can walk to reach the end, which is 4 node, and every node is valid node, so we will keep value 1. That's why we just put 1. For example, I will start DFS over here. Okay, t of 4 is going to be 1 plus maximum of t of left. What's left? Left is going to be 5. I mean, I'm just putting the value 5, don't confuse it with that. I'm just putting a node value 5 comma t of 6. Now this is the recurrence, right? Again, we'll try to compute this particular value and this particular value. When I do this, eventually I will reach the answer. So next, what the recurrence will go, I will also draw the stack table also for you guys to for better understanding. Now this is going to be our call stack. But initially we'll have the node 4. Now we just pop it out and we just return a recurrence relation like this, which is 1 plus max of t of 5 comma t of 6. Now we'll calculate for t of 5, which is going to be the left node. Okay, now we just put it into a call stack. I'm just putting in a call stack. Now we'll just pop this out. Okay, now t of 5 is going to be 1 plus maximum of, what is the maximum of 4 7 comma 3, t of 7 comma t of 3. Okay, now I need to put value 7 in a call stack, right? Let me put 7, and I need to pop this out also. So t of 7, what t of 7 tells? 1 plus, does it have any kind of children, which means we are just ending the base case. If I put left, it's going to be null, right? It's going to be null comma null. And if you remember carefully the base case, so node is null, it will return a 0. So this will look like max of 0 comma 0. So what is max of 0 comma 0? Which is 0, and 0 plus 1, which will return value 1 over here. So now this will become a 1. Okay, now we just finish all these things. Now we are coming to the right part. Now 3 will be in a call stack. So we'll calculate for 3 over here. I'm going to rough this because it's not used for any further calculation. So let me take it out 3 over here. So 3 of 3. What is 3 gives? The same, it's going to be a leaf node. So obviously it's going to return 1 over there. So I'm going to put 1. So what is the max of 1? So max of 1 comma 1, which is 1. And if I add this with 1, this will give 2 answer. Okay, this will give 2. And let's put 2 over here. Okay guys, now we have visited this entire left side and we just compute that 2 is the maximum step you can reach from this particular point. I mean, there is only 2 steps you have to take to reach the end. That's it. Now we have to visit for this particular side, right side. We need to conclude the answer when you reach the all the possible position. So now let's look it for the right side also as well. Now I'm going to put t of 6 into the stack. I'm going to pop this out, and t of 6 is going to be 1 plus maximum of, what is 2 comma 1, t of 2 comma t of 1. Very simple. Now do this process again. I'm going to take the left side, I'm going to put in the stack, and I'm going to calculate for t of 2. T of 2 is going to be again 1 plus maximum of t of 8. We have one right child for one left side, and we have no right child, so just put null. And now we have to calculate for t of 8. You know, t8 is going to be the leaf node, so the value is going to be 1, and null node value of 0. Now what is the maximum? Maximum of 1 comma 0 is 1. And if you add this with this value, this will become 2, and we just traverse back. I mean, if you think about how DFS works, it will reach the end and it will go back and it will reach the right side. So we just go back and we just put the value 2 over here. And now we need to compute for t of 1. You know, t of 1 is also a leaf node, so the value is going to be 1. Put 1. Now if we compute the answer, what is the maximum of 2 comma 1? 2, and add it with the 1, which will become as 3. Sorry, it should be 3. Now it's simple. Now what we have to do, we just traverse back and apply this value. Now tell me guys, the maximum of 2 comma 3. What is the maximum of 2 comma 3? Which is 3. And if you add it with the 1, this will become as a 4. Now we got the answer. It's very simple, right? Just the recurrence relation. 1 plus maximum of left and right. And if I want to tell it very simply, just assume you are standing over here and you are just visiting all the side to conclude which is going to be the maximum length over there. Let me write the pseudocode very quickly. So let's declare the function name of DFS. DFS is going to get the root node. So now what is the base case? If there is no root, right? If root is null, then you can simply return 0. That's base case. Now we need to write the recurrence relation, right? The same one single line, that is return 1 plus maximum of DFS comma root dot left comma DFS of root dot right. That's it. If you don't believe me, this is the entire code. See how much line? 1, 2, 3, 4. That's it. 4 line. It's a very simple code. It's very simple logic as well. If you write down this recurrence relation, you can understand very easily. And yeah guys, now let's see how to solve this problem using BFS. You guys know how BFS works. BFS will work in a way that it will go from level wise. It will first visit this node and it will visit this node and it will visit this node and it will visit this node. But unlike DFS will go like, it will go to the deepest point and the right point, and like this it will go. But if you see BFS, it will go level wise, or it will go like this. So it's very easy to conclude the answer, right? This is going to be level 1, this is going to be level 2, this is going to be level 3, this is going to be level 4. So you can simply return answer as the last level value. Now let's see how to deal with this. Okay, so initially we are setting level is going to be 1. Always a valid node as a level 1, right? So initially level is going to be 1, and we're just using a stack. You know, we are going to use stack for BFS, right? So let's draw the stack tree here. I'm going to put the root node to the stack. I'm going to put the root node to the stack, and I'm going to pop all the values. Not the word, I'm going to pop all the values, because if I reach this particular node, I cannot simply push only one node and I can calculate the level. It's not like that. I have to calculate all possible values. So what I'll do is I'll just append all the child, and then I will pop all the child in next iteration. So now what I need to do, I need to pop this value. I need to put all the children to the queue, right? If I pop the 4, what are the children? 5 and 6. I'm going to put 5, 6 over here. Now we have visited the 1 level. Now we are going to the next level, right? The next level, when I come, I need to pop all the values, guys. Remember, I need to pop all the values. So let me pop all the values. I'm going to pop 5, and when I pop 5, what are the values going to be in a stack, which is 7 and 3. And I need to pop 6 as well. If I pop 6, I'm going to have 2. I'm running out of a space. I'm going to put 1. Now when I pop all the values from the stack, I need to increase the level, which is going to be 2. Okay, I'm going to rough this part. Let me write here very clearly 7. Now we are at the 3rd level, guys. So just remember this, whenever you're going to the next level, you need to pop all the values and put the child into the stack. I mean the queue, sorry, it's a queue, right? Put all the values in a queue. So now we are coming to the level 3. So we are just popping 7. And if any child is there, no. So we don't need to do anything. Same for 3. If you come to 2, for 2 we have 1 child. So append the child, which is 8. And 1 is a leaf node, there is nothing going to be there. And just increase the level to the 3. Very simple. And again, you will come to the last level, which is going to be the fourth level. So when I come to the 8, I'm going to see if any node is there. No node is there. So just pop it out and just empty and increase the level to the 4. It's very simple and very easy. And now let's see how to write the code for this. So let's have a queue, guys. Let's declare a queue first. And before that, now let's check if the incoming node is valid or not. It could be a null node, right? It could be empty tree as well. So if root is none, simply return 0. Do you remember the base case, which is coming from the DFS solution? So simply return 0 over here, return 0. And next, let's declare the queue. So queue is going to be a simple queue, and I'm going to append the root over here. So you can put the root into the queue. And now let's declare the level as well. So level is going to be 1. And because we just take care of the base case initially, we don't need to care about remaining things. So you can write the code in like this. First, check the base case. If the root is null, just simply return 0. If not, then start this process. Just declare a queue and add a root to it, and declare the level as well as a 1, because we have one valid one valid node, which is a level 1. That's why I put level is equal to 1 instead of 0. You can put 0, but it doesn't matter. So just put level 1. And now let's start this process, popping process. While length of queues is not equal to 0, we need to pop until we reach all the nodes. So that's the base case while length is not equal to 0. So if you remember carefully, we need to pop all the nodes in a stack, right? Then only we can tell that we have visited the entire entire level. So let's do that. For I is going to be 0 and I is less than length of a queue, and I plus plus. This will take care of all the node which is in a stack. Now what do you have to do? We have to pop the node, right? So node is going to be q dot pop left. In many language there are different. One language it will be pop q dot pool, and in Python we used to have pop left. Left is nothing but it's taking the first value in a stack. This particular value, leftmost value. That's it. Very simple. So pop left will take the leftmost value, and then it will check if node dot left. If there is a left, push it into the queue. Simple. Q dot append node dot left. Same thing for the right as well. If there is a right node, just push it into the queue. That's it, guys. Very simple. And now what do we have to do? Once we done all this process, we need to increase the level, right? So level is going to be increased to 1, and then that's it. Close the loop, and then a class you can simply return level. That's it, guys. Very simple. I hope you understand both the solution, and I think the video is getting longer. Actually, I'm working on a blog, and there I will provide the code for the iterative DFS solution, because I think it's not needed for explaining right now here. And I will provide my blog. It will be over within few days, couple of days. I will link the blog over here in the future. If you see, you can go to my blog, you can read the solution there also, and I will provide the iterative DFS here, because I think it's no need to talk about all the solution in this video itself, because it's already getting too much late, and whatever we talk, it's optimal one. Oh my goodness, I forgot to talk about the time complexity, right? So the time complexity is going to be similar for both the solution, which is going to be O of n, and space is going to be O of n, or you can tell O of h. H is nothing but the height of a tree. Very simple, O of n, because we are visiting every node once. So the time is going to be O of n, and space is also going to be O of n or O of h. If we want to tell clearly technically, it's going to be O of h, which is going to be height of a tree. That's it, guys. Very simple. And now let's code this up in a lead code. This is very simple code, guys, as we discussed there. So now let's start writing the base case. Always you need to write the base case first for whatever recurrence you're writing, recursion solution. So if not root, if there is no root, you can simply return 0. And if not, we need to write the recurrence relation. The recurrence relation, very simple. Return 1 plus maximum of self dot max depth which is the function name, and root dot left, comma, root dot right, max depth of root dot right. That's it, guys. Very simple code, right? Only 4 lines of code. Now let me run this. Yeah, it passed the test cases, but let's see whether it's passing the all the test cases or not. I hope it does. Yeah, it does. It passed all the test cases. Thanks for watching till this, guys. We'll see you in one more video. Until then, bye.